Okay, today we're going to be looking at square roots as a little bit of a review. Next week we're going to jump into the distance formula, which requires being able to manipulate square roots. So I thought it was a good idea that we could get a jump on that. So what does it mean to take a square root? A square root is a function. It's an operation that you can use on a number, or we could use it with variables. Most of the time in geometry, we are going to be using actual numbers, though, in things like the distance formula. So the square root function finds a number that, when it is multiplied by itself, equals the original argument of the function. So if I say something like the square root of 16, what that function does is find the number 4 because 4 times 4 equals 16. The square root is the inverse of the square function, and this is important when we want to simplify them later. So if I say something like the square root of 2 squared, then the square root and the squared undo each other because they're inverses, and the answer is just 2. And then in geometry, we are usually only interested in what's known as the principal square root. So in algebra, whenever you took a square root, you had plus minus. And that's totally correct. But in geometry, we're usually dealing with things like distances, side lengths, stuff like that. So we only really care about the positive square root. Unless you're told otherwise, just assume that you just want the positive square root in geometry. Okay, parts of the square root. We've got a root b right now. The radical symbol is what you would probably call the square root. It's like the little hat that goes over the radicand. So the radicand is the number or numbers inside of a square root. And then out front, being multiplied by the square root, is the index. So index, radicand, radical symbol. That's our parts. What operations work on a square root? Multiplication always works. So if we have the square root of a times the square root of b, that's equal to root ab. So just like we've got right here, we can just multiply those together inside the square root. When we have indices, that's the plural of index, out in front of them, we multiply the indices together, and then we multiply the radicands together, and then we simplify if we have to. So if we have 2 root a times 3 root b, we multiply the 2 and the 3 together to get 6. We multiply the a and the b together to get ab. So our answer is 6 root ab. We don't mix and match. The indices get multiplied together and the radicands get multiplied together. Division, because it's the inverse of multiplication, seems like it should work about the same way, and it does. So if we have root a divided by root b, that's the same thing as the square root of a divided by b. So we can just combine those. And then when we have indices, when we have an index in front of each square root, that works the same also. So right here we've got 10 root a divided by 4 root b. We divide 10 by 4 to get 5 halves. And then again, we've got the square root of a divided by b. Simplification is the last thing that we can do on a square root, and we'll talk more about that later. But if we have something like the square root of a squared b, remember when I said that squaring and square roots are inverse operations of each other? Well, if I take the square root of a squared, I just end up with a. And then this b, it doesn't have a square on it, so without any further information, we can't do anything with it. So a root b. What operations will not work? Addition and subtraction. If we have the root of a plus the root of b, that is not the same thing. That does not equal the square root of a plus b. And then same thing with subtraction. If we have root a minus root b, that does not equal root a minus b. The only time that we can add or subtract is if we have like radicands. So right here we've got 2 root a plus 3 root a. Because the radicands are like, we can add the indices. So 2 plus 3 is 5, and our answer is 5 root a. That is the only time we can add or subtract. So be careful with that. That's a big mistake that I see pretty often. Simplifying radical expressions. We can use the fundamental theorem of arithmetic. So what that says is that each number, each integer, so we're talking whole numbers, can be represented as a product of prime numbers. Uniquely represented, I should say. So if we have the number 6, it can only be represented by 3 times 2. Since multiplication is commutative, 2 times 3 also works, but that's the same thing. We can't just throw a 5 in there. It doesn't work. Another example would be 24, which we can break down into prime numbers. 24 is 8 times 3, which is 4 times 2 times 3, which is 2 times 2 times 2 times 3. And we can simplify that into 2 cubed, because there were 3 of them, times 3. And that's how we would represent 24 as a product of prime integers. So when we simplify, we can actually use this, and we want to pull out squares. So if we go back to this root 6 is going to be the same thing as root 3 times root 2, because like I said a couple slides ago, we can multiply and we can divide back and forth. But there's no pairs there. Root 3 is a prime, root 2 is a prime. They don't mix and match, so root 6 does not simplify. The answer is just root 6. Root 24 is a little bit different. So we know that root 24 is the same thing as the square root of 2 cubed times 3. We want to take out squares. So since I have 3 2's, I'm going to take out 2 of them. So I've got the square root of 2 squared times root 2 times root 3. Well, the square root of 2 squared is the same as 2. And then the root 2 and the root 3, we can't simplify anymore. So our final answer is going to be 2 root 6. So that's how we would simplify that one. We are looking for squares. We want to take out, once you get good at it, you want to take out the biggest square that you can. But until then, just break it down. Let's practice just a couple of these. I just pulled up Khan Academy here. Khan Academy is not your homework, but I knew that they would have some random questions for me. So we want to simplify. We want root 50. Well, I know that the square root of 50 is equal to some product, and what I want to do is I want to take square numbers out. So my squares are 1, 4, 9, 16, 25, 36, 49, so on and so on. I want to look for perfect squares. Well, 25 does multiply into root 50, or into 50. So I've got 25 times 2, and 25 is the same as 5 squared. So when I'm taking the square root of a square, I can say that that's 5. Square root of 25 is 5. And then the root 2 we can't do anything with, so we can say 5 root 2. And then we'll put that in as the answer, 5 square root of 2, hit check, and hey, we got it right. Let's do one more. So we want the root of 72. So this might be one that we have to break down a little bit. I'm not seeing anything right off the bat. Actually, I kind of do. But I don't know what the biggest square root is going to be out of here. So let's just take 72 and let's break it down. Now, here's a trick with multiplication. If the 2 digits of a number add up to something that's divisible by 9, then that is, the whole number is also divisible by 9. So I know that 9 is going to be able to go into 72. So I'm going to have 9 times 8. That's going to be my 72. 9 is a perfect square. So I'm going to just hang loose with that one right there. 8 is not, but let's see if we can break it down into something that is. 8 is 4 times 2. 4 is also a perfect square. So that means that the square root of 72 is going to be the same thing as the square root of 9 which is 3, times the square root of 4, which is 2, and then times whatever we have left over that's not a square pair. So the square root of 2. So our final answer is going to be 6 root 2. So in the checkbox here, I'm going to punch in 6 root 2, and it should tell me that I am correct. Okay, we'll get some practice on this in class. Make sure you bring me any questions. Have a good night.